today, so before starting the lecture, I talk a little bit about the arrangement. Probably in the first lecture, Professor Shou mentioned about the subject arrangement or not. It is, right. So actually, I think one thing we need to pay attention is that the assessment of this subject is rather special, rather different. And we do not have a formal written examination. Yeah, but we have a test. The test, in-class test, is written. And the final examination, there's no final, there is a final examination, but it's oral. It's not written, so it's very unusual. Yeah. And the arrangement we will give you later. So, and we have for the assessment, we have two continuous assessment. We have two parts. One is a student seminar, right? You will give one. You will group up, right? And then you will have give a presentation and give a seminar, submit a seminar report. So this, and together with the in-class test. So that's all for the in-class test. And then for the continuous assessment. But for the final examination is oral. So you will be interviewed by two lecturers and with on two topics. And one topic is your selection among the 10 topics concerned in the subject. And another subject is assignment. It's not your choice. So you got two topics to meet, two lectures. And one is your choice. You can choose one out of the 10. And but another one is assigned by us in some means. Right? So then you will meet two lecturers. Typically, we say about 8 minutes per person because we have too many students today. So that is the physical arrangement. And so if you are clear, then we will very. I think next week or the week after we will make the arrangement for your seminar topic. And today we talk about development of smart energy station and energy flexible. Because the lecture notes I used here is not particularly prepared for the subject teaching. So it is basically something from the keynote speech in different parts. This one, right? And there are some ones also, some ones from next lecture, some ones from. And I already uploaded this in the backboard. There's a PDF file uploaded. Today we talk about, in my past, I have two sessions, and I'll talk about two topics. And one topic is talk about building energy flexibility, and another is talk about building energy efficiency. For building energy efficiency, there will be two parts. One part is how to optimize the design of energy systems, and the second is how to the optimal control of energy systems for buildings. So these two together, we talk about is for the energy efficiency of buildings. And another part, as I mentioned, is energy flexibility of buildings. So you will find, if you look at my profile, and we concern many different buildings and applications. But basically, we talk about my the efforts I involved is actually I can group it in three main categories. One in terms of performance, in terms of I talk about energy efficiency for energy saving and talk about energy transferability for carbon neutrality. And but what is the methods and technology we concern? It's about smart technologies. So that is basically my area of expertise. So today we talk actually, as I said, this title is for the keynote in somewhere. So this part is talk about energy flexibility, don't talk about energy efficiency. And you know, in the old days, we talk about sustainability of buildings. We talk about energy efficiency. We talk about how to provide the expected services which reduce the energy inputs. So that is the you say we have so many things to do in buildings for I think so is to provide the expected service with minimal energy costs, energy input. So that is basically the things. But so then in the old days, when we talk about energy issues in buildings, we talk about energy saving, improve energy efficiency. But in the last 10 or more years, energy efficiency is not enough. Why? Because now we talk about the carbon neutrality of the entire human society, right? So if the people, the human beings need to have the carbon neutrality, then for the power systems, the energy use of human, right, is today is the mean of the carbon emission sources, carbon emission sources. So if we want to achieve carbon neutrality, then the carbon neutral power system is the basis. And for the carbon neutral power system, then we need to the key thing is we need to have to replace the renewable generation, to replace the traditional fuel cell, those energy sources which cause serious carbon emission by renewable generation. But to do so, in buildings, because when we have this, when we do that, there are a lot of challenges, and the buildings can actually. So I will talk about my concern, because for Hong Kong, and I think you may pay a little attention, because when you talk about you present something and you write something, you need to pay attention to describe what is the scenarios of your technology and your study. So here in my team, in my group, and because we are in Hong Kong, and our emphasis is the buildings in high density cities. So those are large buildings and the high density cities. So we are talking about here. I will talk about the what could be the roles and the contributions of buildings to the carbon neutrality in high density cities. And so then, what are the challenges, right? And particularly, what is the contribution? And then we talk about the main technologies for buildings to contribute to the carbon neutrality. And another thing, so that is this part I talk about. So the roles of you can have a look on the regular means for carbon neutrality, because if you go back the 20 years or even just 15 years back, so in that time we already considered to talk about carbon neutrality. In that time, when we talk about carbon neutrality, the people mostly consider that we have efficiency, and to reduce the input efficiency, demand side, to reduce the demand side, so to reduce energy consumption. And another side is you increase the renewable generation of the supply side. But of course, also in the demand side, because you have building inequalities and distributed renewable generation. So that is actually in the demand side. So we talk about if we group it into locations and by locations or by the distribution, then renewables can be also in the demand side. But when we talk about generation and supply, certainly renewable generation is in the supply side. And so in the old, say 10 years or 15 years back, just two things. That is, reduce the demand and increase the renewable generation. So we think it will be done. But actually, in practice, we find, in the last 10 years, we find, if you just do these two, and that may cause big problems because of the mismatch between the supply, the mismatch of supply and demand. So the reason is the renewable generation, the renewable energy cannot be controlled. Right, the renewable energy is good. It's very good because it has no environmental impact. It's free, right, because from the nature. But there's something very bad. It is because the renewable is intermittent. The renewable is uncontrollable. So that caused so that the renewable energy, the renewable generation comes. So you got to use it, and when you need, there's maybe no, or there's not enough. Such as you talk about wind energy. So the wind energy, sometimes you got strong wind, and sometimes you do not have sufficient wind, right? And for solar also, solar is we cannot control it. It's controlled by the God. So you have the day and night change, but you also have clouds and things. So there's several effects by the weather and conditions. So therefore, just have generation and reduce more generation and reduce the energy demand is not sufficient, and far from sufficient. And to do so, then the regular solutions for to address this supply-demand mismatch problems, that is to introduce the storage, the power storage or energy storage or in the power system. So then the typical power energy storage for the power systems, such as pumped storage, right? So you talk about hydraulic generation, typically such as if you talk about the generation, the hydraulic power plants, such as in the three gorges, and in the west, particularly southwest of China, there's a lot of hydraulic power plants. Now those hydraulic power plants is for the renewable energy, for the hydropower generation. But some power plants, hydraulic power plants, is specially built as a storage. So if in the power system you have surplus power, then you pump the water up to some level. And when there is there is lack of power, then you use the water to to generate power. So this power plant is this we call it pumped storage. So that's actually the hydraulic power storage. And battery storage is one important new technologies. Actually, battery is not new, but the popular use, large-scale use of battery storage is new. And there's another. So this is already practical, and the green hydrogen is another issue. And so those are the means to enhance, to improve, increase the storage capacity. But this means a lot of investment and a lot of cost. And for instance, hydrogen storage is not mature yet. And pump storage, you need a lot of investment, and also you need big spaces. There's a damage to the environment. And battery is still not cheap, right? The price is going down, still not cheap. But one thing is battery, you need some special materials, and another thing is that the battery actually the use the battery, how to treat it, and that's still another issue. So in all those things, so that means it's a cost, it's environmental issues, and another is from the. And another issue is this storage cannot solve all the problems of power supply and demand mismatch. And I will talk about this later, because when we talk about demand, so when you talk about, we need to understand a little bit of the power system operation, because for in general, if you do not consider the setup of power system, you may say, okay, the power system have sufficient supply or have lack of power supply. But actually, you will find that because of the power system is large, and the power system is not just one node. So you have sufficient power in some part of the power system, but may not be sufficient in another part of the system, because power system in Hong Kong, and because Hong Kong power system is small. So in general, and another thing is the Hong Kong's size is also not big. So therefore, actually the power distribution capacity in Hong Kong is rather large. So therefore, in general, if you have sufficient power supply, it's almost, you have everywhere sufficient, almost. But cannot be exactly sure. Why? Even in Hong Kong power system, and you know, we still have distribution. For instance, particularly you say today, in the future, we have more and more EV charges. And why we have more and more EV charges? Because the EV charge is a very huge demand if it's in use. And but the existing power distribution system in the low level, in the district level, or in the building level, and there are some limit. Even for if the EV charges is added to the existing facilities, or to the existing building, to the existing power distribution system, and so once suddenly there's a large number of EV charges included in use, then the power demand in a particular location. We talk about particular location is one, is associated with the power distribution system, is associated to the transformers at different level. So you may say, okay, so this, for the EV charges for today, is for one EV charge is easily goes to 100 kilowatts for one, right? But if you, and then later on, because I talk about, I discussed with the power companies and the developers for charging, they are developing terrible technology. It's terrible. They are, of course, it's very good for the users, but it's very bad for those service providers like us. Right, we are providing the building the energy facilities, but it's very much harmful to us. For instance, now they are talking about to have the EV chargers, which can up to 1,000 kilowatts. For 1,000 kilowatts for EV charge, but not yet in the market, but they are in the test. You can be sure that will be available in some time. So you say if one EV charge, the instantaneous power is up to 1,000. But if you talk about this building, the whole building, the demand, I think it's about 1,000 in the full load, 1,000 kilowatts. But if you got one EV charge, if this one EV charge in this building it is going to charge, then your power is doubled. But if you have 5 together, so you can imagine if you have 5 such a EV charge is connected to this building, but then suddenly if you use this at the same time, then the power supply facilities cannot support this, right? So therefore, not just the overall balance of demand and supply is one issue for the power balance, but there's another issue is the local distribution, and so this is in Hong Kong are such a small power system, but in the mainland, the power system is network, the power grid is very large. If you remember, in one case, I think I forgot exactly at the time. It's about a few years back in Sichuan province, because Sichuan province, their power supply is closely associated. They very much depends on the hydraulic power generation. But in one summer in Sichuan, I think it's 5 years back or sometime, the power grid there is seven like of power supply. It's because there's no sufficient wind, right? The wind, the hydraulic generation because of no rain in that time. So then the power supply in Sichuan area is seriously sufficient. Because I visited there one time, and they told me that it's a very bad situation because there's no sufficient power supply. Many industry production have to stop. But in that time, in other places in China, there's sufficient. There's no big problem. But because this region has problem, and so therefore the reason in that time why such happened, because there's no sufficient power transmission to deliver, to transmit the power from another part of the country to this region. So you imagine that in the Chinese mainland, because it's a national facilities, and in China, so we have two power grids, big power grids. One is the national power grid, so that is in the north part, the main part. But there's another part, is South China power grid, so that is the 8 provinces in the south. But even so, the power grid is connected. The Sichuan power system is not isolated with another part of the national power grid. But the distribution capacity is not sufficient. You have power in other places, but you cannot deliver to them. So therefore, so the power balance of the power generation and supply, power supply and demand balance is very certainly in time scale, right? And another, because the power, electrical power, and another energies, for instance, the gas. If you talk about the gas, we do not talk about. You may talk about okay, in every day if you have a balance, right? So today you have so much consumption and how much supply you can have to provide the gas, to provide the fuel. But for the power, the electrical power, the balance is instantaneous. So it's every second and every millisecond you have to balance because electrical is such a different nature, right? So therefore, we have in a time scale we have to be balanced every time, and in the locationally, right? From different locations in the space scale, so you also need to have balance. You have supply somewhere, but this supply may not be able to deliver to another place. Another is, as I mentioned, the power grid have sufficient, because the power supply is also they have distribution, right? The whole grid globally is sufficient, is balanced, but to a particular user, to a particular power distribution system, that may not be sufficient. And this sufficiency depends on one thing is the transformers, the capacity, and another is because you have a distribution system, there's cables, switches, which have capacity limit. So for that, because of this reason, so the storage, because you want to ensure the balance, because in the old days, generation and supply balance is relatively easier to achieve, because the generation is controllable. Because traditionally we have the hydro, nuclear, and we have coal-fired or the gas-fired thermal generation. Particularly the thermal generation, the controllability is very good. But when we talk about the carbon neutrality, the first target we want to phase out is this thermal power plant. And the thermal power plants play a very important role in balancing the demand and the generation demand. But they are the targets to be replaced. And so therefore we need to have increase the capacity. But there are two reasons why we need to increase the capacity of storage. One reason is we have more and more renewable energy generation, which is not controllable, is in the middle. And the second is because of the reduced thermal power plant. Because thermal power plant is originally the balanced capacity, right? And but they are reducing, and eventually they will be phased out. And so then we have to increase the storage capacity. But increased storage capacity is not only the global, because you say, okay, increase the storage capacity in one location, you consider the power grid as one node. So it matters the storage is installed in what location, right? Including in the high level, which location you install it in Shenzhen area, or you install it in Guangzhou area, or you install it in Yunnan province. So it's different. And another is you install the capacity in a high level or in a low level of the distribution system. Because as it's in a low level, they are still in the power grid, you may have sufficient, but in the low user side may not be sufficient because we're limited to power generation. But this is particularly an issue in the end user side, the balance issue. Yeah, I think there are two things. One thing is the increase the use of EVs. The EV is a very bad user. EV is very, it is encouraged because EV is supposed to be, EV itself is not environmentally friendly, not at all. But EV is prepared for if the power grid, the power generation is carbon free, so then the vehicle is carbon free. But if the electricity is not carbon free, then the EV is not, there's no benefit. Right? So then, but because the EV have a potential to support the carbon free power grid, but the EV itself is a very bad habit because when you charge it, it's very it causes huge dynamics, huge fluctuation of power use in the demand side, in the end user side, right? And so therefore, traditionally we talk about the power distribution system in a low level, and because there was a problem, but the problem is not so serious, compared with the large number of EVs introduced in the demand side. Because EV can be, when you talk about air conditioning, you talk about such as cooking, you talk about those things. So you see in one period of time you have more users. So then the energy is changing and it's dynamic. But one for EV is more dynamic because the EV is very powerful. And EV is not always in use. When you charge it, it's very high demand. And so that for the power systems, for power distribution system, that is the same thing. We want the demand to be flattened because then we can have a high efficiency of use, and you do not need to invest a high capacity, because when you have a short period of time, you have a very high demand, then you have to invest a lot for the capacity. But you invest for the capacity, you do not use it, so it's a very bad investment. And for instance, actually in Hong Kong, the power company's profit calculation is based on the investment. It is just an example, a bad example. And in Hong Kong, because the power company in Hong Kong is private, but power supply is essential. But then the government and the power companies have some contract agreement, and the agreement in traditional is the total investment plus the operational cost to get that is the investment cost, right? And the energy price, the electricity price is according to the agreement, is the investment together with the operational cost at a profit margin, so that's 10%. So this forms the electricity price, and for the investment, the power companies like to invest more, because if they invest more, then the investment is higher, then the profit can be higher, right? So therefore, in Hong Kong, even the power company is private, but the investment of the power company need to approved by the government. Otherwise, they will invest a lot, then the price will go up. And so for that reasons, so the power balance in the temporal scale and the power balance in the time-wise and location-wise is both methods. So then, for the building side, so in the power systems, you see, we have for the storage, and actually in the power system there is one research area is about the storage, optimized allocation of energy storage. So it's to what in the for the renewable generations in the generation side, they are required to have some storage. In the power grid, there is also storage, and in the distribution network, there are storage to be invested. And in the demand side, we also is also encouraged to have storage. So this is a matter of how big storage capacity and where to allocate the power storage. So that's the issue, and this is the issue of the power grid optimization. But in the demand side, we were also there's also a need of energy storage, and for buildings, we actually to make use the energy storage capacity of buildings. It is one option to solve the problem of demand and supply balance in the power systems. As I said, there is a need of storage in different locations of the power grid. So therefore, it is only invest in the supply side or in the power network, power systems, the grid side is not sufficient, and it is also is not the best way to do it. So then in the buildings, in the demand side, we also encourage to use to make use of the energy storage capacities. So this is we talk about. In the mainland China, they talk about they are encouraging a term called renewable storage, direct DC, and flash energy. So I do not have a translation there, and this is because this is a Chinese term. It's not in the West, such as in Europe and in the North America, they talk about this term. So they talk about 光储直流 is it's the renewable and storage DC and the flash infinity. And for that, and I have some concern to that because one thing is very good because this definition and this move actually attracted the attention of the national energy policy makers. Actually, 光储直流 this technology is already adopted by the what's the name of this? It's actually by the state, right, as a policy. But technically, this term is not perfect because one thing is these four items forgot the efficiency, right? they talk about the renewable generation, they talk about storage, they talk about the transmission, the means of power transmission. But they do not talk about reduce the demand, is efficiency, increase efficiency, reduce its basic. And so in the in states, actually they talk about two things. They talk about reduce demand and increase the energy flexibility of buildings. And renewable, of course, is another one thing. Renewable, if possible, we can introduce renewables even in the buildings in the district. So therefore, if DC is another issue, and DC is a very serious issue, but it's another issue. DC is even a bigger issue compared with flexibility, because when we talk about DC is this is a fundamental challenge of the power transmission. Because you talk about you remember that's starting to use electricity. I forgot it. I think it's about 200 years. That may not be so long. It's between 100 and 200 years. So when we talk about DC, but when we talk about the electricity use, so in that time you have a choice. Is you use DC or you use AC. Right. And you use DC or AC. And eventually in that time we choose the AC. Why we choose AC? There are two issues. One issue is the user, the consumer, energy consumer. For energy consumer, you know that one thing. Two type of energy users, consumers. One thing is this lamps. You know, in the very starting, the lighting is the basic. So for the lamps in lamps, AC/DC doesn't matter. Right. So then, and another thing is those motors, electrical motors. So which one is more convenient? This DC motors or AC motors? And so that's one issue. But this DC AC motors, it is a technology already 100 years ago is already solved issue. But in that time, what is the key issue? That time we choose AC for power systems. It is because of transmission. Because when you have the power transmission, you have to change the voltage. You increase voltage for long distance transmission, but when you in the demand side, when you receive the high volt, then you have to reduce the voltage to deliver to the end users. So this is the transformer. The transformer in the traditional transformers, the DC transformer is very difficult and it's not possible to have a big scale. So therefore, in that time, because AC transformer is very easy. AC transformer is very easy. You just have the cores. No high tech. So that is the reason. But today, the DC transformer is easy already. That's not an issue, because now it's already in the long distance transmission. They already use DC because DC has the advantage of low energy loss, because DC is the constant current. AC you have the current changes, right? So in the time scale, the efficiency of using DC is not so high efficiency, because quite a time the capacity of cables is not in use. But DC you can have a continuous, and also DC, the AC you have this kind of changes of power currency and the direction. So that will generate those electromechanical fields. There's some distribution. So altogether today, DC use is in principle is better. Another very important thing. So in the transmission generation side, because in generation side, the the previous generation is DC already, original DC. But in another side, in the user side, many of the modern consumers are DC, such as this is DC. The end user is this. The user is CPU is a DC user. But when you receive the AC, you have to transmit, convert it to DC for the end use. So therefore, but to change the power system transmission from AC to DC is very, very a big issue. Because I remember 20 years ago, I forgot what the reason I was invited to attend a discussion workshop of the power system on the choice, the transaction between AC to DC. It's a big discussion there, and the people have the wish, but it's very difficult to do it because it's like one thing is much easier. For instance, in Hong Kong, we drive in the wrong side. What is your country? The same side. So you have the American system, yeah, and so here in Hong Kong, there is the British system, So even in Hong Kong, just change the wrong driving side. It's very difficult. It's much easier to change the facilities compared with change the AC to DC. But even so, it's very, very, very difficult because the transport facilities to change from the wrong direction to the right side is not easy. Right. But for DC AC it's also difficult. So therefore I suggest, so we don't worry about the AC DC applications for buildings today because that is a big issue. And actually, if we develop energy flexible buildings, we do not need to have AC. We can have energy flexible buildings, DC-based energy flexible buildings. We can have AC-based energy flexible buildings. So it's not mixed up AC and DC issues with energy flexible buildings. So therefore, I propose to have Guangxiao, that is renewable. Efficiency and flexible. Because one reason is the flexible and storage is repeating. Flexible is the overall, is the storage itself is a part of the flexibility. So storage actually is one mean of flexibility is storage. So in the building sectors, when we talk about energy buildings, there are different ways terms. One, today we often use energy flexible buildings, and we also use grid interactive buildings, and also use grid responsive buildings. My team started to do energy flexible building research. In that time, there is no common agreed. When we published the first paper 15 years ago on this, my team, myself, is the very first team to do building energy flexibility research in building sector, because energy flexibility in the demand side. This research, this concept started in the grid side, power grid side. And in the building side, we do the technical solutions, technologies for buildings to be energy flexible. Our team and myself are the very first team in the world. And so when we published our first few papers, at that time I chose between grid interactive and grid responsive buildings. But in that time, I said, because great interactive buildings, that means it sounds to me that a building and a grid are at the same level. So I talk to you and you talk to me, right? So it's interactive and in more equal. But in that time, I was quite surprised. I said, okay, building and grid, it is interacting, but basically grid is dominating, and then we are in the side to follow. And it's two directions in the reaction, but they are the master, and we are the service provider. And so therefore, in that time, I think, to be polite, we are not so much aggressive, but we chose the grid responsive building. But finally, we find in the last 10 years, particularly because of the U.S. Ministry of Energy, MOE, right? They choose to use grid interactive building. So therefore, I find now you search the literature, more publications use grid interactive, and grid responsive buildings still there. There is a percentage of people still use grid responsive, but less. So today, if you find our later publications, I use grid responsive or grid and energy flexible buildings. I use very often today. The energy flexible buildings is more layman. It's easier to understand by layman, by the bigger domain, and by the public. And grid responsive and grid interactive is more technical. So it's but nowadays the grid interactive building is more commonly used in the profession. So I made a wrong choice at this time. But the grid responsive building is still in use. There you can find that's still percent. I do not make a calculation. Probably 20% of publications still use grid responsive. And so when we talk about energy flexible building, actually, if you talk about in the European countries, they use more energy flexible buildings. They use more the general technology. But in the U.S., particularly the U.S. Ministry of Energy, they use great interactive and efficient buildings because they are public. The national strategy, there is a document. The term is great interactive and efficient buildings. So that is the term used by the national strategy of the Ministry of Energy. So so grid responsive buildings, I think is in US they more use grid interactive buildings, right? And so then, but to me, it means the same thing. Doesn't matter energy flexible buildings, grid interactive buildings, or grid responsive buildings. This means the same thing. That refers buildings which can reduce the power use without unacceptable compromise in service quality. And when the power grid is short of power supply, and stored energy when there is power surplus power supply. So then this is the issue. Right? Actually, you know, one way, this capacity of the human beings, the capacity of storage is reduced significantly. Why you want to have a look of the wild animals, such as tiger, the lions. Their energy storage capacity, their flexibility is very much big compared with people. I think the human beings, if you go back to 10,000 years back or or more, our flexibility of taking food should be much flexible. You see, if you take the look at the storage, you see the life of the wild animals. When they have food, they eat a lot, and when there's no food, then a couple of weeks they have no food, where they can still survive. But today, so for human beings, you say, okay, so today you do not have lunch, so you suffer a lot. But if you do not have lunch, you do not have dinner, then you cannot work at all, right? Right. But this is now for buildings. We have to recover and have to restore the energy flexibility, because we do have energy flexibility. Just like people, we have the inherent flexibility, by the way, for body, and we got to restore and we got to reuse, to recall this flexibility. But one thing we need to pay attention is, without unacceptable compromise. Often we have some compromise, but when we provide flexibility, we will minimize the compromise, the interference to the impact to the service quality, but they may have some impact. We just, when we talk about energy flexibility or energy efficiency, so without the service quality considered, energy flexibility can be 100%. But we just stop the energy use. So that's absolutely flexible, right? So when we talk about energy saving, we stop the energy use, stop all the machines alight, then save 100%. But this is not our intention, because we need to provide the right service. So the difficult of providing flexibility and the difficult of energy saving is because we have to maintain the expected services, right, in terms of human comfort and in terms of industrial production. So that is the difficult, and this is the challenge. Okay, how to achieve carbon neutral transformation of power system in high-density cities? And I think some of you in this classroom, and some of you in the faculty in the department, and you talk about renewable energy applications. I understand some of you may work in the centralized renewable energy generation, and some of you in the renewable energy side, you may work in the distributed, particularly building integrated renewable energy, and this should be encouraged. And but the application we need to pay attention on the limitations of applications. Personally, I encourage if the buildings are low-rise, if the buildings are particularly in the remote site, not in the city center, particularly high-density city centers. In the high-density city centers, because of the high-rise buildings, and lot of buildings close together, so you do not have much resources of renewable. Wind, you cannot use it because it's terrible, it's not possible. You have the wind turbine in somewhere in the cities is not allowed. And for PV, because if you high density buildings and buildings close together, high rise, you have a little bit smooth area, and then you install the PVs, which is not energy, it's not cost effective. And another reason is it causes many problems. For instance, you take an example in Hong Kong, the roof area is very valuable. The roof area is, you have a PV there, but you can be, there's a much valuable, high valued use for the roof, right? And you use the, if you use, myself very much against the building integrated PV applications in high density cities. I talk about high density. If you go to the low density cities, you go to the, if you have a house, then PV application is very, very effective. But of course, if you have a luxury house, you will not care too much. But of course, ordinary houses, but in high density, you see, if you talk about buildings 40 floor high, and such a tower, roof area is very small and very expensive, and for use, very expensive for other, very valuable for other things. And if you use the windows for and the facade for PV application, and that is not clever, not wise, because you install it, you may say, okay, I can have the same cost, the same price as windows. That is possible, not too much expensive. But when you install it, you maintain it. If 5 years later or some years later, you got to replace it. How you do it? It's high-rise building. It costs a lot for replacement. It's still very, very, very expensive. In the first installation, may not be so difficult, but when you install it, you maintain it, it's very expensive. Let's take an example. You know, the buildings of what's the building? Our innovation tower is the boat just ahead of us. The maintenance, the building is built to be economical. It's a low-cost building, the three block. For the development, it's a low cost. For maintenance, three block building is economical. The cost is not. But you talk about the boat building, right? The innovation tower, very expensive to build it. But you say you build it is expensive. It doesn't matter. Some people pay it, but to maintain it, very expensive. Why is so expensive? Because of the glasses. It's so different. Every piece of glass is special design. Because of a special shape, the sealing of the glass is not so good, not easy, not good. And then there's leakage. So to maintain it is very difficult because of the leakage. So you can imagine that you have this PV in a high-rise building. But if you say you have a house, 2 or 3 floors, it doesn't matter. But if you have a 40, 50 story building, you have the windows and the envelope, the structure with PV. Is not a smart idea for not just for installation but also for the maintenance. So therefore, for those, as I said, we encourage the PV applications in the low-rise buildings, in the low-density regions, and but in the high-density regions, the role is that. So to achieve the carbon neutrality within buildings or cities is not practical, not cost-effective. That is, so we carbon neutrality have is I myself always suggest the carbon neutrality have to do it beyond the city, outside the city. That's first thing. And then do it, if possible, to be centralized. Because scale is efficiency, and scale is operational efficiency, maintenance efficiency, and the investment efficiency. So if we can have the scale, you have centralized PV farmers, right? and centralize the wind farmers. So then, in terms of energy, in terms of investment efficiency, in terms of operational maintenance efficiency is higher. So therefore, we say, what are the rules and contribution of buildings in high-density cities? Is reduce energy demand first, right? And contributing to the grid power balance for high overall renewable penetration. So we reduce the energy use, so that is our basic rule. And the second is we provide the flexibility. We use buildings as a storage to support the overall supply-demand balance of the power grid, and therefore to facilitate the use of renewable generation at large in the power grid at large. So that is what I think we should do. In fact, you know, I had the chance of renewable such as PV applications in Hong Kong. 10 years back, 15 years back, I was very much encouraged in that time because the people do not aware that PV can generate energy. Right? So in buildings, if we install some PVs, I remember in the campus, near the which building is the building with the bank with the bookstores. In that, I think 20 years back, I think 25 years back, my colleague, Dr. Yang, installed a PV in there. So it is very good, right? Because that's educating, show that this is possible, the technology available. But this is for sure. And but you really seriously talk about the energy use, energy generation is not meaningful, because in this campus, every year we have over 100 million Hong Kong dollars for electricity in this building, in this campus, 100. So 100 million Hong Kong dollars. So this is because in Hong Kong the price is easy to calculate. It's about 1 kilowatt per 1 kilowatt for $100. So 100 million Hong Kong dollars electricity bill is about 100 million kilowatt hour. So if you talk about in this area, if you have 100 square meters PV, how much you can generate? It's not much. It's totally economical. And actually, I think in Singapore, because Singapore government is very effective. They enforce the use of PV generations in cities. But they do not. I think that they did everything they can do. The percentage of generations far below 1%. So it's not much meaningful in terms of practical impact. But in terms of society, say the educational issues is good. But we say we show here in cities for people, but we got to build the real plants outside the city. Right. So that is centralized generations, and in the cities we got to reduce energy use, and we got to provide, to make use of buildings as flexibility, as a capacity resource. So you see, and we have the energy efficiency with demand, we have energy flexibility. So we have a stop of 10 minutes, so that we continue.